Good Friday, March 27th, 1964. The clock reads 5:36 in the afternoon, and across southern Alaska, the day feels completely ordinary. Schools are empty because of the holiday. Many businesses have closed early. Families are preparing to spend the evening together, and the streets of Anchorage are quieter than they would normally be. Then the ground begins to move. At first, the vibration feels familiar. Earthquakes are not unknown in Alaska, and many residents expect the shaking to disappear within seconds. But it does not stop. The movement becomes stronger. Buildings sway, windows break, and roads begin rolling beneath vehicles. People rush into the streets, only to discover that the ground outside is moving just as violently as the structures they have escaped. For 4 minutes and 38 seconds, the earth refuses to become still. Entire neighborhoods slide toward the sea. Downtown streets collapse. The soil opens into enormous cracks. Underwater slopes fail, ports disappear, and sections of the coastline rise or sink permanently. Offshore, immense quantities of water are being displaced. Some waves are created by the movement of the ocean floor. Others are produced by underwater landslides directly beside coastal communities. Within minutes, walls of water begin advancing toward villages that have no sirens, no evacuation system, and almost no understanding of what is coming. The earthquake will eventually be measured at magnitude 9.2. It will become the strongest earthquake ever recorded in North American history, and the second largest instrumentally measured earthquake anywhere on Earth. Only the Great Chilean earthquake of 1960 was stronger. But what happens on this single afternoon will do more than destroy buildings and reshape Alaska. It will provide scientists with some of the clearest evidence ever found of how the surface of the planet actually moves. How could one earthquake transform thousands of miles of coastline? Why were some communities given hours before the tsunami arrived, while others were destroyed within minutes? And how did a disaster in one of the most remote parts of the United States help settle one of the greatest scientific debates of the 20th century? To understand the answer, we must return to Alaska as it existed before the earthquake. A young state on an unstable coast in 1964, Alaska was the newest state in the United States. It had joined the Union only 5 years earlier and was still developing its identity. The state covered an enormous territory, but its population was smaller than that of many medium-sized American cities. Most residents were scattered across isolated coastal towns, islands, forests, mountain regions, and distant interior communities. Anchorage was Alaska's largest and fastest-growing city. Modern storefronts, theaters, hotels, new neighborhoods, and expanding roads gave the city the confidence of a frontier boomtown. 4th Avenue formed the center of the commercial district, where shops and businesses reflected the optimism of a young state expecting rapid growth. Farther south, towns such as Valdez and Seward depended on their ports. Freighters delivered cargo. Longshoremen worked along wooden docks. Railroads carried goods inland, while fuel tanks, canneries, warehouses, and shipping facilities stood close to the water. Across Prince William Sound, smaller fishing communities occupied remote bays. One of them was Chenega, an Alaska native village where families had lived for generations. Life followed the rhythm of the sea, the fishing seasons, the canneries, and the long northern winters. March was a relatively quiet period. Many fishing crews had not yet returned for the summer, so the harbors held fewer people in boats than usual. That fact, together with the Good Friday holiday, would prevent the death toll from becoming even greater. The residents trusted the land beneath them. Science, in many ways, trusted it as well. Before plate tectonics was accepted today, scientists understand that the outer surface of the Earth is divided into enormous tectonic plates. These plates move slowly across the planet. They can separate, slide past each other, or collide. In some places, one plate is forced beneath another in a process known as subduction. In 1964, however, plate tectonics was still a developing and controversial theory. Some scientists supported the idea that continents moved, but many respected geologists remained skeptical. Researchers had discovered deep ocean trenches, underwater mountain ranges, patterns of earthquakes, and evidence of new crust forming on the ocean floor. These discoveries suggested that the surface of the Earth was dynamic, but direct evidence showing exactly how one plate could descend beneath another during a major earthquake remained limited. Most people, including many scientists, still imagined the crust as far more fixed and stable than it actually was. There was also little understanding of tsunami danger among the general population. The word tsunami was not commonly used in the United States. People often spoke of tidal waves or seismic sea waves. No effective tsunami warning center protected the southern Alaska coast. There was no extensive network of sirens, sensors, or public evacuation routes. Coastal residents had no system capable of rapidly identifying a massive earthquake and warning every threatened town. Beneath Prince William Sound, meanwhile, centuries of geological pressure were approaching their limit. The plates break free. The southern coast of Alaska lies above a major subduction zone. Here, the Pacific Plate moves toward the North American Plate and is slowly forced beneath it. The movement does not always happen smoothly. Friction causes large sections of the boundary to become locked. Even while the plates remain stuck together, the Pacific Plate continues pushing forward. The rocks above the boundary begin to bend. Energy accumulates year after year, generation after generation. The crust behaves like a giant compressed spring. People live above this process without seeing it. Cities grow, roads are built, and ports operate, while the pressure remains hidden deep below the surface. At 5:36 p.m., the locked section finally breaks. The Pacific Plate and the North American Plate suddenly move past one another. The bent crust snaps back in a process known as elastic rebound. The rupture does not happen at only one point. It begins tearing along the plate boundary for hundreds of miles, almost as if the seabed is being unzipped. Different sections of the fault break one after another beneath the cold northern sea. This enormous rupture explains why the shaking lasts so long. Many earthquakes end after several seconds, because the damaged section of the fault is relatively small. In Alaska, the rupture continues traveling, releasing energy for nearly 4 uninterrupted minutes. As seismic waves spread through the region, Anchorage begins to collapse. 4 minutes of destruction. Anchorage is located approximately 75 miles from the epicenter. The first movement arrives as a low, rolling vibration. Residents pause and wait for it to weaken. Instead, the ground begins rising and falling like the deck of a ship in rough water. People run from buildings and struggle to remain standing. Some hold onto streetlights and parked cars, while the pavement moves beneath them. Along 4th Avenue, cracks spread through the road. One side of the street begins dropping away from the other. A section of the commercial district sinks by nearly 9 feet, carrying stores, sidewalks, and building fronts downward. Windows shatter, signs tilt, walls lean. The modern center of Anchorage folds along a widening failure in the ground. At the airport, the control tower sways beyond its limits and collapses, killing the air traffic controller inside. At Government Hill, the soil fails beneath a school building. The structure is severely damaged, but the Good Friday holiday has left it empty. Had the earthquake occurred during a normal school day, the number of victims might have been much higher. The shaking continues for approximately 4.5 minutes. The earthquake releases vastly more energy than the famous 1906 San Francisco earthquake. Its effects are felt across a huge area. The movement is detected hundreds of miles away and reaches southeast into British Columbia. More than 1,000 miles away in Seattle, the newly constructed Space Needle sways as the seismic energy arrives. Water oscillates in lakes, rivers, wells, and swimming pools as far away as Texas and Louisiana. The entire planet vibrates. Sensitive instruments record the Earth resonating like a bell long after the main rupture has ended. In Anchorage, however, the greatest damage is not caused by shaking alone. A hidden weakness beneath one residential neighborhood is about to transform solid ground into something that behaves like liquid. When the soil lost its strength, Turnagain Heights was one of Anchorage's most attractive residential neighborhoods. It stood on a bluff overlooking the water, with homes, streets, yards, and gardens built on land that appeared stable. Beneath the neighborhood were layers of fine marine clay and water-saturated sediment. Under ordinary conditions, the material supported the structures above it. During several minutes of violent shaking, that changed. When certain saturated soils are shaken strongly enough, the particles can lose contact with one another. The water between them begins carrying the pressure, and the soil suddenly loses much of its strength. This phenomenon is called liquefaction. The ground may look solid, but it begins behaving like a heavy liquid. In Turnagain Heights, the weakened bluff starts sliding toward the sea. The neighborhood breaks into massive blocks. Roads split apart. Backyards disappear. Houses tilt, collapse, or move downhill with the sliding earth. Some homes travel hundreds of feet. Others are torn apart where they stand. Approximately 1 square kilometer of land is transformed into a chaotic landscape of collapsed slopes and enormous cracks. As many as 75 houses are caught in the failure. The destruction becomes one of the most studied earthquake-triggered landslides in history. Engineers learned that a well-designed building can still be destroyed if the soil beneath it becomes unstable. The disaster changes the way cities investigate the ground before constructing homes, roads, hospitals, and schools. But while Anchorage is collapsing, a faster and more deadly danger is forming along the coast. The waves created beneath the harbors. Southern Alaska contains steep fjords and coastal towns built on river deltas. Over centuries, rivers had deposited large quantities of loose sediment near the shore. When the earthquake struck, many of these underwater deposits became unstable. Enormous masses of sediment collapsed into deeper water. These submarine landslides pushed the water aside, generating powerful local waves. Unlike a tsunami crossing an entire ocean, these waves formed directly beside the towns they would destroy. Some arrived in only a few minutes. Others struck almost immediately. No warning center could have acted fast enough to protect everyone standing directly above the collapsing underwater slopes. Valdez was one of the most heavily affected communities. Valdez disappears into the water. Valdez had been built at the end of a deep fjord on a delta composed of loose sediments. Its waterfront was the center of the local economy. When the earthquake began, a freighter had recently arrived, and residents gathered near the dock to watch it being unloaded. Then the underwater face of the delta collapsed. A massive volume of sediment slid into the depths, dragging part of the harbor and dock with it. The water pulled away from the shore and then returned violently. A local wave struck the port within moments. The dock was destroyed, and approximately 30 people near the waterfront were killed. There was no practical warning. The wave had been created almost directly beneath them. Survivors described the sea withdrawing as though taking a breath before returning as a wall of water. Later studies showed that the waves traveled far up the inlet and reached extraordinary heights. Valdez survived as a community, but geologists determined that its original location was unsafe. The town would eventually be rebuilt several miles away on more stable ground. Other communities faced similar destruction: Whittier, Seward, and Chenega. Whittier was a small community of around 70 people. Local waves struck its shoreline, damaging buildings and killing several residents. At Seward, the earthquake ruptured fuel storage tanks along the waterfront. Fuel spread across the port and caught fire. At the same time, waves and underwater landslides struck the harbor. Burning fuel moved across the water, while flooding carried debris over rail yards, docks, and industrial facilities. The town faced fire and water at the same time, but the greatest proportional loss occurred in Chenega. The Alaska Native village stood low beside a quiet bay. Its homes and church were clustered near the water, where families had lived for generations. Only minutes after the earthquake, an enormous wave entered the bay. There were no sirens, no warning messages, and almost no time to reach higher ground. The water swept through the community and carried away nearly every building. Approximately 1/3 of Chenega's population was killed. For decades, The exact source of the wave remained uncertain. Later, research connected it to a huge underwater landslide on a steep slope hidden beneath the nearby water. In the first minutes after the earthquake, these local landslide-generated waves caused most of the deaths in Alaska, but the movement of the tectonic fault had also produced a second type of tsunami. This wave would travel across the entire Pacific. The tsunami crosses the ocean. As the fault ruptured, a vast area of the ocean floor moved vertically. Some sections rose, while others dropped. Where the seabed lifted, it pushed the entire column of water above it upward. The displaced water spread outward in every direction. In deep water, a tsunami can travel at speeds similar to a passenger aircraft. Its wavelength is enormous, but its height offshore may be small. A ship at sea might cross the wave without noticing it. The danger increases when the tsunami reaches shallow coastal water. It slows down, compresses, and rises. The water then advances inland in a series of powerful surges. Kodiak Island was among the first major areas struck. The sea withdrew and returned repeatedly. Fishing boats were torn from their moorings and carried into the streets. The waterfront was transformed. The tsunami continued across the Pacific. It reached Hawaii and was recorded as far away as New Zealand and Antarctica. Distance gave faraway communities something the towns near Prince William Sound did not have: time. Some locations had several hours before the waves arrived. However, the warning system of 1964 was too slow and incomplete to use that time effectively. It took observers more than an hour to estimate the location and scale of the earthquake. Warnings moved slowly and did not always reach the people who needed them. The consequences became especially severe in Crescent City, California. The wave that arrived late Crescent City was a small lumber and fishing town on the northern California coast. Its harbor and low downtown area were highly vulnerable. More than 4 hours after the Alaska earthquake, the first waves reached the city. Some residents moved away from the shore. Others approached the water to watch. The first surges did not appear catastrophic. The sea rose and fell, and after several waves, some people believed the danger had passed. They began returning toward the harbor. But a tsunami is not one wave. It is a series of surges, and the largest may arrive later. A stronger wave entered the harbor and swept through the low downtown area. Buildings, vehicles, boats, and debris were carried inland. 12 people were killed. Crescent City suffered the greatest loss of life caused by the tsunami outside Alaska. The tragedy demonstrated one of the most important rules of tsunami survival: never return to the coast after the first wave. The water may continue rising and falling for hours, and a later surge may be the most destructive. Why the death toll was not higher. The earthquake and its waves killed more than 130 people across Alaska, Oregon, and California. Considering the extraordinary magnitude of the event, the number was surprisingly low. Several factors reduced the death toll. Alaska was thinly populated. Many buildings were constructed from wood, which could flex better than heavy brick or unreinforced masonry. The earthquake occurred during a holiday, when schools were empty and many offices had closed early. March was also outside the busiest fishing season, meaning fewer workers and boats were in the ports. Only a small number of victims were killed directly by collapsing buildings or the shaking itself. Most were killed by the waves. Timing, geography, construction style, and chance prevented the disaster from becoming even more deadly. The first night when the main earthquake ended, evening was approaching. Large parts of southern Alaska had lost electricity and telephone service. Roads were broken. Bridges were damaged. Communities were isolated. The temperature was falling toward freezing. Aftershocks began almost immediately. During the first 24 hours, 11 aftershocks stronger than magnitude 6 struck the region. Every new movement terrified survivors and threatened already damaged structures. Smaller tremors continued for more than a year. The outside world did not yet understand the scale of the disaster. Many communities had no road connection to the rest of the state, making immediate rescue extremely difficult. The first response came from local residents. Neighbors searched damaged buildings for survivors. Workers restarted generators. Doctors and nurses treated the injured with limited equipment, sometimes working by flashlight. Families opened their homes to people who had lost everything. Blankets, food, stoves, and shelter were shared. Radio operators became the communication network of the broken region, sending information about missing people and damaged communities. There was no single hero. There were thousands of ordinary decisions to help. At first light, bush pilots flew over isolated towns and villages. Their reports revealed the true geography of the destruction. Federal and military assistance arrived later, but the first night belonged largely to the people of Alaska. A coastline permanently transformed. When daylight returned, residents and scientists discovered that the earthquake had physically changed the land. Across tens of thousands of square miles, parts of the coast had risen or fallen. On Montague Island, some areas were uplifted by as much as 36 feet, or approximately 11 meters. Reefs and shorelines that had remained underwater for centuries were suddenly exposed. Marine organisms were left stranded far above the new tide level. Elsewhere, the land had sunk. Forests and fields were invaded by saltwater. Near Kodiak and Homer, the sea reached farther inland than before. Some harbors became too shallow for the boats that had once used them. Channels familiar to fishermen were altered. New land appeared where there had previously been water, while other areas disappeared beneath the sea. Whole islands had moved vertically. The coastline had been redrawn in one afternoon. For residents, the changes created enormous practical problems. For scientists, they created an extraordinary record of what had happened beneath the earth. The geologist who followed the evidence. Among the scientists sent to study the altered landscape was George Plafker of the United States Geological Survey. Plafker and his colleagues traveled across the damaged coast, measuring where the land had risen and where it had fallen. They examined old tide lines now positioned above the water. They studied drowned shorelines, exposed marine organisms, damaged ports, and submerged forests. As thousands of observations were collected, a clear pattern emerged. A broad belt near the ocean had been uplifted. A parallel region farther inland had subsided. The pattern was too large and too consistent to be random. Plafker asked what single movement could explain both uplift and subsidence across such an enormous area. The evidence pointed toward one mechanism. The Pacific Plate had moved beneath the North American Plate along a gently sloping fault. Before the earthquake, the locked plate boundary had bent the overlying crust. When the fault broke, the upper plate rebounded. Some sections moved upward and toward the ocean. Other sections dropped. That same movement displaced the seabed and generated the ocean-crossing tsunami. The Alaska earthquake had revealed subduction in direct, measurable form, the earthquake that helped prove plate tectonics. Before 1964, plate tectonics remained a developing theory. After the earthquake, scientists possessed one of the clearest real-world examples of a major subduction event. The uplift and subsidence matched the expected movement of a convergent plate boundary. The earthquake's location matched the offshore trench and seismic zone. The deformation of the coast showed how the upper plate had been bent, while the boundary remained locked. Elastic rebound explained the earthquake. The vertical movement of the seafloor explained the tsunami. One mechanism connected all the evidence. The tectonic plates were real. They moved. One plate could descend beneath another. When a locked plate boundary suddenly broke, it could shake a region for several minutes and send waves across an entire ocean. Plafker's research became essential to the modern understanding of megathrust earthquakes. The 1964 Alaska earthquake became one of the most important textbook examples of a subduction zone event. A remote and thinly populated coastline had helped reveal one of the main forces shaping the planet. From disaster to protection, the lessons did not remain inside scientific journals. The tsunami showed the need for faster detection and better communication. Communities near the earthquake source would always have very little time, but distant towns could receive warnings if the earthquake were identified quickly enough. Tsunami monitoring systems were expanded. A regional warning center was developed to locate major earthquakes and send information across threatened coastlines. Over time, new seismometers, Tide gauges, ocean sensors, communication systems, and public alerts improved the process. The word tsunami entered common use. Coastal residents learned a rule paid for with human lives. If the ground shakes strongly or for a long time, immediately move to high ground. Do not wait for a siren. Do not approach the coast to watch the water. And do not return after the first wave. The destruction in Anchorage also changed engineering. Turnagain Heights showed that the strength of a building means little if the ground beneath it fails. Soil studies, liquefaction risks, landslides, coastal subsidence, and seismic design became more important in urban planning. Building codes were revised. Valdez was rebuilt on safer ground. Chenega was eventually re-established in a new location. The earthquake caused more than $300 million in damage in 1964, equivalent to billions of dollars today. But its deepest legacy is measured in the lives later protected by stronger buildings, better planning, and faster warnings. The Earth is still moving. The tectonic process beneath Alaska did not end in 1964. The Pacific Plate continues moving beneath the North American Plate. Stress continues accumulating along different sections of the subduction zone. Similar boundaries exist around the Pacific, including Japan, Indonesia, Chile, and the Pacific Northwest. These regions are capable of producing the largest earthquakes and tsunamis on Earth. Today, scientists monitor them with seismometers, satellites, ocean sensors, and computer models. But no instrument can stop the plates from moving. Preparation can reduce the consequences, but it cannot remove the geological danger. The Earth follows a calendar much longer than human memory. A fault can remain quiet for generations. Cities grow during that silence, and people begin believing that the danger has disappeared. But silence does not necessarily mean safety. It may mean that pressure is continuing to build. The Good Friday earthquake was not only a disaster in Alaska, it was a planetary event. Anchorage's commercial district collapsed. Turnagain Heights slid toward the sea. Valdez lost its waterfront. Seward burned and flooded. Whittier was struck by local waves. Chenega lost approximately 1/3 of its people. Kodiak saw boats carried into its streets. Crescent City was devastated more than 4 hours later. The tsunami crossed the Pacific and was detected as far away as New Zealand and Antarctica. More than 130 people were killed. Thousands lost homes, businesses, and access to basic services. Some parts of Alaska rose by as much as 36 feet. Other areas sank beneath salt water. Forests were flooded. Harbors changed depth. Islands moved, and the coastline was permanently altered. Yet from that destruction came a new understanding. The earthquake provided direct evidence of subduction. It helped confirm that the Earth's surface is divided into moving tectonic plates. It revealed how the largest earthquakes form, and how movement of the seabed can send tsunamis across entire oceans. It changed geology, engineering, emergency planning, construction standards, and tsunami warning systems. It also exposed the fragility of one of humanity's most basic assumptions. We call it solid ground because it remains still during most of our lives. We build homes, roads, schools, and entire cities upon it. But beneath the surface, the planet is always moving. On March 27, 1964, that hidden movement became visible. For 4 minutes and 38 seconds, the land behaved like water. Neighborhoods moved. The sea rose. The coastline changed. And when the shaking finally ended, humanity understood the planet beneath its feet more clearly than ever before.